Right now, as you watch this video, light that has traveled for over 13 billion years is hitting sensors on a telescope floating 1.5 million kilometers from Earth. That light carries information that should not exist. It shows galaxies that are too massive, too structured, too impossibly mature to be there. According to every model we have built over the past century, these galaxies are breaking the rules of cosmic evolution. And the scientists who spent their entire careers refining the Big Bang Theory are now facing an uncomfortable truth. Either our understanding of the universe's birth is fundamentally wrong, or something we thought was constant, dark matter, gravity, time itself, behaves in ways we never imagined. In July of 2022, the James Webb Space Telescope began sending back its first deep-field images. Within weeks, astronomers noticed something disturbing. Galaxies designated Glass Z13 and Sears 93316 appeared in regions of space corresponding to just 300 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it is an eye blink. To put this in perspective, imagine compressing the entire 13.8 billion year history of the universe into a single 24-hour day. The Big Bang happens at midnight. These galaxies appear at 12:03 a.m. In that brief window, they had somehow assembled billions of stars, formed spiral structures, and achieved masses comparable to our own Milky Way, a galaxy that took over 13 billion years to reach its current form. The problem is not just that these galaxies exist early. The problem is that they exist at all. Current cosmological models predict a specific timeline for structure formation in the universe. First, tiny quantum fluctuations in the primordial plasma. Then, dark matter begins to clump under gravity, creating gravitational wells. Normal matter falls into these wells. Gas clouds collapse. The first stars ignite. These stars live, die, and seed space with heavier elements. Slowly, over hundreds of millions of years, the first small galaxies form. They merge. They grow. This process is gradual, constrained by the speed of light, the density of matter, and the expansion rate of space itself. But Glass Z13 does not fit this timeline. It contains an estimated 1 billion solar masses of stars. To assemble that much matter, to convert gas into stars at the necessary rate, to do all of this in just 300 million years, the math does not work. Not with our current understanding of star formation efficiency. Not with the known density of matter in the early universe. Not with the cooling rates of primordial gas. Astrophysicist Alison Kirkpatrick at the University of Kansas described the discovery as Rohan Naidu at the Harvard-Smithsonian Center for Astrophysics called these objects. These are not sensationalist terms. These are careful scientists using language that reflects genuine crisis. Now, imagine you are a cosmologist who has spent 30 years refining simulations of the early universe. You have accounted for dark matter halos, baryonic feedback, reionization epochs, metallicity gradients. Your models reproduce the cosmic microwave background with exquisite precision. They predict the large-scale structure of galaxy clusters we observe today. They match supernova data, gravitational lensing measurements, the abundance of light elements. Everything fits. And then, James Webb shows you a galaxy that, according to your models, should not exist for another 500 million years. What do? You check the data. You verify the redshift measurements. You recalculate the photometric analysis. And when everything checks out, you are left with three possibilities. Your distance measurements are wrong, your understanding of galaxy formation is wrong, or your cosmological model is wrong. Let us address the first possibility. Redshift, the stretching of light as space expands, is how we measure cosmic distances. The farther away an object is, the faster space is expanding between us and it, and the more its light shifts toward the red end of the spectrum. For Glass Z13, the measured redshift is approximately 13.1. This corresponds to light that has been traveling for over 13 billion years. Could this measurement be wrong? Possibly. High redshift galaxies are faint, and their spectral features can be ambiguous. Dust can redden light, mimicking cosmological redshift. But James Webb uses infrared sensors specifically designed to peer through dust. It measures multiple spectral lines, not just one, and multiple independent teams have confirmed these redshifts using different methods. The probability that all these measurements are systematically wrong in the same direction is vanishingly small. So if the distances are correct, we move to the second possibility. Our models of galaxy formation are incomplete. Perhaps stars formed much more efficiently in the early universe than we thought. Perhaps the first generation of stars, population 3 stars, made of pure hydrogen and helium, were far more massive than current models predict, burning brighter and dying faster, seeding space with metals at an accelerated rate. Perhaps gas cooling mechanisms we do not fully understand allowed clouds to collapse more rapidly. These are plausible adjustments, but they require pushing parameters to their absolute limits, and even then, the numbers barely work. You would need star formation efficiencies approaching 100%, meaning nearly every atom of gas converts into stars, with almost no waste. This has never been observed in any galaxy, at any epoch. It violates everything we know about feedback mechanisms, where stellar winds and supernova explosions blow gas out of galaxies, regulating star formation. Which brings us to the third, most unsettling possibility. The Big Bang model itself needs revision. Not abandonment. Let us be clear about this. The Big Bang theory is supported by overwhelming evidence. The cosmic microwave background, the abundance of hydrogen and helium, the expansion of space, the evolution of galaxy populations, all of this fits. But quote 2 is not a single monolithic idea. It is a framework built on assumptions about dark matter, dark energy, the initial conditions of the universe, and the laws of physics themselves. If any of these assumptions are wrong, the framework shifts. Consider dark matter. We have never directly detected a dark matter particle. We infer its existence from gravitational effects, the rotation curves of galaxies, the motion of galaxy clusters, gravitational lensing. We assume dark matter is quote underscore 3 underscore, meaning its particles move slowly and clump efficiently under gravity. But what if dark matter is not cold? What if it interacts with itself in ways we have not accounted for? What if its properties changed over cosmic time? Some physicists are now proposing quote 4 or quote 5 models that could allow structures to form faster in the early universe. These models are speculative, but they are being taken seriously because the alternative, that our entire cosmological framework is wrong, is even more radical. Then there is the possibility that the universe is older than we think. The current estimate, 13.8 billion years, comes from measurements of the cosmic microwave background by the Planck satellite, combined with observations of distant supernovae and the large-scale structure of galaxies. But these measurements depend on assumptions about the expansion rate of the universe, known as the Hubble constant. And here is where things get interesting. Different methods of measuring the Hubble constant give different answers. Measurements based on the cosmic microwave background suggest a value of about 67 kilometers per second per megaparsec. Measurements based on nearby supernovae suggest about 73. This discrepancy, known as the Hubble tension, has persisted for years. If the true value is higher than we think, the universe could be younger. If it is lower, the universe could be older. An older universe gives more time for galaxies to form, potentially resolving the James Webb anomalies. But it also means recalibrating every cosmic timeline we have constructed. Some cosmologists are going even further, questioning whether the expansion rate of the universe has been constant. What if dark energy, the mysterious force driving the accelerated expansion of space, was weaker in the early universe? What if it strengthened over time? This would mean the early universe expanded more slowly than we thought, giving structures more time to form before being pulled apart by expansion. Or conversely, what if there was a brief period of rapid expansion, beyond the initial inflationary epoch, that we have not accounted for? These ideas sound exotic, but they are being published in peer-reviewed journals by respected physicists. And then, there are the truly radical proposals. A small but vocal group of scientists is suggesting that the Big Bang model, while correct in broad strokes, is missing a crucial chapter. What if the universe underwent a phase transition in its first few 100 million years? A moment when the fundamental forces or particle properties shifted? What if the laws of physics themselves were slightly different in the immediate aftermath of the Big Bang? This is not science fiction. We know that the universe has undergone phase transitions before. When the universe was a trillionth of a second old, the strong nuclear force separated from the electroweak force. When it was a millionth of a second old, quarks combined into protons and neutrons. When it was 380,000 years old, electrons combined with nuclei to form neutral atoms, releasing the cosmic microwave background. Each of these transitions changed the behavior of matter and energy. Could there have been another transition we have not detected, one that temporarily accelerated structure formation? The scientific community is divided. Some researchers are confident that the James Webb anomalies will be resolved with better data and refined models. They point out that early observations are always messy, that photometric redshifts are uncertain, that spectroscopic follow-up will likely revise some of these distance estimates downward. They remind us that in the early 2000s, astronomers thought they had detected galaxies at redshift 10, only to later realize those objects were closer and less remarkable. Caution is warranted. But others are not so sure. They note that James Webb is not finding one or two anomalous galaxies. It is finding dozens. They point out that the telescope's instruments are performing exactly as designed, that the data quality is unprecedented, that multiple independent analyses are reaching the same conclusions. They argue that dismissing these observations as measurement errors is wishful thinking. And they remind us that science advances not by confirming what we already believe, but by confronting observations that challenge our models. What makes this moment particularly fascinating is that it is happening in real time, in public view. In previous eras, scientific revolutions unfolded over decades, confined to academic journals and conference halls. But today, preprint servers like Archive allow researchers to share results immediately. Social media enables instant debate. The James Webb data is publicly available, meaning anyone with the skills can analyze it. This democratization of science is both exhilarating and chaotic. Theories proliferate, speculation runs wild, but beneath the noise, a genuine scientific process is unfolding. Hypothesis, observation, revision, debate. So where does this leave us? Are we witnessing the collapse of the Big Bang theory? No. The Big Bang framework, that the universe began in a hot, dense state and has been expanding and cooling ever since, is not in question. The evidence for this is too strong. But the details, the specific mechanisms, the timeline, the nature of dark matter and dark energy, these are all open for revision. And that is not a weakness of science. It is its greatest strength. Science is not a collection of eternal truths handed down from on high. It is a process, a method for refining our understanding of reality through observation and experimentation. Every scientific theory is provisional, subject to revision in light of new evidence. Newton's laws of motion worked perfectly for centuries, until we discovered they break down at very high speeds, leading to Einstein's relativity. Einstein's relativity worked perfectly, until we discovered it breaks down at quantum scales, leading to quantum mechanics. And now, quantum mechanics and relativity themselves are incomplete, unable to describe what happens inside black holes or at the moment of the Big Bang. This is not failure. This is progress. The James Webb discoveries are forcing cosmologists to confront the limits of their models, and in doing so, they are opening new avenues of inquiry. Perhaps dark matter is more complex than we thought. Perhaps the early universe was more dynamic. Perhaps there are feedback mechanisms or physical processes we have not yet imagined. The next few years will be critical. More data will arrive. Spectroscopic measurements will confirm or revise the photometric redshifts. Simulations will be refined. New theories will be proposed and tested. And slowly, painstakingly, we will converge on a more accurate picture of cosmic history. But here is what you should take away from this. The fact that scientists are panicking is a good thing. It means they are honest. It means they are not clinging to dogma. It means they are willing to follow the evidence wherever it leads, even if it upends decades of work. This is how science is supposed to function, not as a rigid orthodoxy, but as a flexible, self-correcting system that adapts to new information. And the universe, as always, is under no obligation to make sense to us. It does not care about our models or our equations. It simply is. Our job is to observe it as carefully as we can, to build the best explanations we can with the tools we have, and to remain humble enough to admit when we are wrong. The James Webb Telescope is showing us a universe that is stranger, more complex, and more wondrous than we imagined. And that, ultimately, is why we build telescopes in the first place. Let us now turn to the galaxies themselves, not as abstract data points, but as physical objects with properties that defy explanation. Glass Z13 is not alone. Sears 93316, initially thought to be even more distant, has been joined by a growing catalog of what astronomers are calling _6_. Each one presents its own puzzle. Each one forces us to confront a different aspect of our cosmological assumptions. Take Glass Z13 first. When astronomers analyzed its spectral energy distribution, the way its light is distributed across different wavelengths, they found something unexpected. This galaxy is not just massive, it is red. In astronomical terms, red means old. Blue galaxies are dominated by young, hot stars that burn bright and die fast. Red galaxies are dominated by older, cooler stars that have been around for a long time. But Glass Z13 exists just 300 million years after the Big Bang. Where did it get old stars? To have a significant population of red stars, you need stars that formed even earlier, lived out their lives, and then settled into a stable, mature population. This pushes the timeline back even further. If Glass Z13 contains stars that are already old at 300 million years, those stars must have formed at 100 million years, maybe even 50 million years after the Big Bang. And that is a problem, because at 50 million years, the universe was still in the so-called, '7, a period when the first stars were just beginning to ignite, when space was filled with neutral hydrogen that absorbed ultraviolet light, when conditions were hostile to rapid star formation. Now consider the structure. Glass-Z-13 is not a chaotic blob of stars. It shows signs of organization, a central bulge, possibly a disk. This implies rotation, gravitational settling, dynamical equilibrium. These are features that take time to develop. When galaxies first form, they are messy, irregular, dominated by turbulent gas flows and violent star formation. Over hundreds of millions of years, they settle down. Gravity pulls them into more ordered shapes. Spiral arms emerge. Central black holes grow and regulate star formation. But Glass Z13 appears to have skipped this messy phase entirely, or compressed it into an impossibly short timescale. Then there is CEERS 93316. Initial photometric analysis suggested a redshift of 16.7, corresponding to just 230 million years after the Big Bang. If confirmed, this would make it the most distant galaxy ever observed. But subsequent spectroscopic follow-up has been inconclusive. Some measurements suggest the redshift is lower, perhaps around 4 or 5, which would place it much closer and much less problematic. But other measurements support the high redshift. The uncertainty itself is revealing. It shows how difficult it is to measure distances to these faint, ancient objects. It also shows how easy it is for confirmation bias to creep in. Researchers who believe the Big Bang model is robust are more likely to favor the lower redshift, while those who suspect the model needs revision are more likely to favor the higher one. This is not dishonesty, it is human nature. And it is why science requires multiple independent measurements, peer review, and time. But let us assume, for the sake of argument, that CEERS 93316 is indeed at redshift 16.7. What does that mean? It means we are seeing this galaxy as it was just 230 million years after the Big Bang. At that time, the universe was still reionizing, the process by which the first stars and galaxies emitted enough ultraviolet light to strip electrons from neutral hydrogen atoms, making space transparent. Reionization is thought to have taken several hundred million years. But if massive galaxies like CEERS 93316 existed at 230 million years, they would have contributed to reionization much earlier than expected. This has implications for the entire thermal history of the universe. It affects the cosmic microwave background. It affects the distribution of neutral hydrogen. It affects the formation of the first quasars. One anomalous galaxy does not just break one model, it sends ripples through the entire cosmological framework. And these are not the only galaxies causing trouble. In October of 2023, a team led by Ivo Labe at the Swinburne University of Technology published a paper identifying 6 massive galaxy candidates at redshifts between 7 and 11. These galaxies, if confirmed, have stellar masses between 10 billion and 100 billion solar masses. To put this in perspective, our Milky Way has a stellar mass of about 60 billion solar masses, and it took over 13 billion years to reach that size. These galaxies achieved comparable or greater masses in less than 700 million years. The paper's title was blunt: A population of red candidate massive galaxies at redshift greater than 5 in Sears. The word candidate is important. These are photometric redshifts, not spectroscopic, so there is uncertainty. But if even half of these candidates are confirmed, we have a serious problem. Labe and his colleagues ran simulations to see if existing models could produce such massive galaxies so early. They pushed every parameter to its limit. They assumed maximum star formation efficiency. They assumed minimal feedback from supernovae and stellar winds. They assumed dark matter halos that formed earlier and grew faster than standard models predict. And even with all these optimistic assumptions, they could only reproduce about 10% of the observed number of massive galaxies. The rest remain unexplained. So what are the alternatives? If the standard cosmological model cannot explain these galaxies, what can? Let us explore some of the proposals that are now being seriously debated in the astrophysics community. First, there is the idea of supermassive primordial stars. In the very early universe, before any stars had formed, space was filled with pristine hydrogen and helium. No heavy elements, no dust, no molecules to cool gas clouds efficiently. Under these conditions, the first stars, population 3 stars, could have been enormous, perhaps 100 or even 1,000 times the mass of our Sun. These stars would have burned incredibly hot and bright, fusing hydrogen into helium at a furious rate. They would have lived for only a few million years before exploding as supernovae, seeding space with the first heavy elements. But what if some of these stars were even more massive? What if, under certain conditions, gas clouds could collapse directly into stars of 10,000 or even 100,000 solar masses? Such stars would be so luminous that a single one could outshine an entire galaxy. And when they died, they would not explode. They would collapse directly into black holes, leaving behind seeds for the supermassive black holes we observe at the centers of galaxies today. This idea is not new. Astrophysicists have been discussing direct collapse black holes for years. But the James Webb observations have given it new urgency. If the early universe contained a population of these supermassive primordial stars, they could have accelerated structure formation in several ways. Their intense radiation would have ionized surrounding gas, triggering secondary waves of star formation. Their deaths would have injected energy and heavy elements into the interstellar medium, enriching it faster than expected. And the black holes they left behind would have acted as gravitational anchors, pulling in gas and stars to form the first galaxies. This scenario is speculative, but it is testable. If supermassive primordial stars existed, they should have left signatures in the chemical composition of the oldest stars we can observe today. They should have affected the reionization history of the universe in ways we can measure. And James Webb, with its infrared sensitivity, might be able to detect their direct descendants, intermediate mass black holes lurking in the centers of ancient galaxies. Second, there is the possibility of modified gravity. Einstein's general relativity has passed every test we have thrown at it, from the precession of Mercury's orbit to the detection of gravitational waves. But it has never been tested at the extreme conditions of the early universe. What if gravity behaves differently when space is very young, very dense, and very hot? What if the gravitational constant itself was different in the first few 100 million years after the Big Bang? This might sound absurd, but it is not without precedent. We already know that the fundamental forces of nature have changed over cosmic history. In the first fraction of a second after the Big Bang, the electromagnetic force and the weak nuclear force were unified as a single electroweak force. As the universe cooled, they separated. Could something similar have happened with gravity? Could there have been a phase when gravity was stronger, allowing structures to form faster, before settling into the strength we measure today? This idea is controversial, and for good reason. Changing the strength of gravity has cascading effects on everything from the formation of atoms to the expansion rate of the universe. It would require rewriting not just cosmology, but fundamental physics. But some theorists are exploring it anyway, because the alternative, that our observations are systematically wrong, seems increasingly unlikely. One version of this idea is called emergent gravity, which proposes that gravity is not a fundamental force, but an emergent phenomenon arising from the quantum entanglement of space itself. In this framework, the properties of gravity could vary depending on the state of the universe. Another version involves extra dimensions, the idea that our three-dimensional space is embedded in a higher dimensional structure, and that gravity can leak into these extra dimensions under certain conditions. These theories are highly speculative, but they are being taken seriously because they make testable predictions. If gravity was stronger in the early universe, it would leave imprints on the cosmic microwave background, on the distribution of galaxies, and on the properties of gravitational waves from the early universe. Third, there is the idea of early dark energy. We know that dark energy, the mysterious force causing the accelerated expansion of the universe, dominates the cosmos today. It makes up about 68% of the total energy density of the universe. But we do not know what it is or where it came from. The simplest model, called the cosmological constant, assumes dark energy has been constant throughout cosmic history. But what if it has not been? What if dark energy was stronger in the early universe, then weakened, and is now strengthening again? Or what if there was a brief period, in the first few 100 million years after the Big Bang, when dark energy was temporarily weaker, allowing gravity to pull matter together more efficiently before expansion took over? This idea, called early dark energy, has been around for a while, but it has gained new attention in light of the James Webb observations. If early dark energy existed, it would have several effects. It would change the expansion rate of the early universe, giving structures more time to form. It would affect the sound waves propagating through the primordial plasma, altering the pattern of the cosmic microwave background. And it would change the growth rate of density fluctuations, allowing dark matter halos to form earlier and grow faster. Some models of the amount of early dark energy has to be just right. Too much, and it would have left obvious signatures in the cosmic microwave background that we do not see. Too little, and it would not solve the problem. Still, the fact that a single modification can address multiple puzzles makes it an attractive hypothesis. Fourth, there is the possibility that dark matter is not what we think it is. The standard model of cosmology assumes dark matter is cold, meaning its particles move slowly and clump efficiently under gravity. This cold dark matter model has been incredibly successful at explaining the large-scale structure of the universe. But it has problems on small scales. It predicts more small satellite galaxies around large galaxies than we observe. It predicts denser cores in galaxy centers than we measure. These discrepancies have led some physicists to propose alternatives. Warm dark matter, where particles move faster and smooth out small-scale structure. Self-interacting dark matter, where particles collide and scatter, preventing dense cores from forming. Or fuzzy dark matter, where particles are so light that their quantum wavelengths are large, smearing out structure on small scales. Could any of these alternatives explain the James Webb observations? Possibly. If dark matter interacts with itself, it could have behaved differently in the early universe, when densities were higher and collisions more frequent. This could have allowed dark matter halos to form earlier, providing gravitational wells for normal matter to fall into sooner than expected. Or, if dark matter is warm, it could have suppressed the formation of small halos while allowing large halos to form earlier, leading to a top-heavy distribution of galaxies in the early universe. These ideas are speculative, but they are testable. Different dark matter models make different predictions about the distribution of galaxies, the properties of gravitational lensing, and the structure of the cosmic web. James Webb, by mapping the distribution of galaxies at high redshift, can help distinguish between these models. And then there's the most radical possibility of all, that the Big Bang was not the beginning. What if the universe existed before the Big Bang? What if the Big Bang was not a singular event, but a transition from a previous state? This idea, called the bouncing universe or cyclic cosmology, proposes that the universe undergoes endless cycles of expansion and contraction. In this model, the Big Bang was not the birth of space and time, but a moment when a previous contracting universe reached maximum density and rebounded into expansion. If this is true, then the structures we see in the early universe might not have formed from scratch after the Big Bang. They might be remnants or echoes of structures that existed in the previous cycle. This idea is not mainstream, but it is not fringe either. It is based on serious theoretical work in quantum gravity and string theory, and it makes testable predictions. If the universe bounced rather than began, there should be signatures in the cosmic microwave background, subtle patterns that differ from the predictions of standard inflation. There should be correlations in the distribution of galaxies that reflect the pre-bounce state. And there should be limits on how far back we can see, a cosmic horizon, beyond which information from the previous cycle has been erased. James Webb cannot directly test this idea, but it can provide data that constrains it. If we keep finding galaxies that are older and more massive than the Big Bang model allows, the bouncing universe hypothesis will become harder to ignore. Now, let us address the elephant in the room, the reaction of the scientific community. How are cosmologists responding to these discoveries? The answer is complicated. On one hand, there is genuine excitement. This is what scientists live for: observations that challenge existing models, that force us to think harder and deeper. On the other hand, there is caution, even skepticism. Many researchers are waiting for more data before drawing conclusions. They point out that photometric redshifts are uncertain, that spectroscopic follow-up is needed, that early results are often revised. They remind us that in the history of astronomy, many anomalies have turned out to be measurement errors or misinterpretations. But there is also a third reaction: anxiety. For some cosmologists, especially those who have spent decades refining the standard model, these discoveries are deeply unsettling. They represent a potential unraveling of a framework that has been extraordinarily successful. And there is a fear, rarely spoken aloud but palpable, that if the Big Bang model needs major revision, it will undermine public trust in science. In an era of misinformation and anti-science sentiment, the last thing scientists want is to appear uncertain or divided. But here is the truth. Uncertainty is not weakness. It is honesty. And division is not chaos. It is the natural process of scientific debate. Consider the history of cosmology. In the 1920s, when Edwin Hubble discovered that the universe is expanding, many scientists resisted the idea. Einstein himself initially rejected it, calling it his biggest blunder. But the evidence was overwhelming, and eventually, the scientific community accepted it. In the 1960s, when the cosmic microwave background was discovered, it confirmed the Big Bang model and silenced most remaining skeptics. But even then, there were debates about the details, the rate of expansion, the density of matter, the nature of dark matter. These debates were not signs of failure. They were signs of a healthy, self-correcting scientific process. Today, we are in a similar moment. The broad framework of the Big Bang, that the universe began in a hot, dense state and has been expanding ever since, is not in question. But the details are being scrutinized, revised, and debated. And that is exactly what should happen when new data arrives. Science is not a static body of knowledge. It is a dynamic process of inquiry, constantly refining our understanding in light of new evidence. So what happens next? Over the coming years, James Webb will continue to observe the early universe, building up a larger and more detailed catalog of high redshift galaxies. Spectroscopic measurements will confirm or revise the photometric redshifts. Astronomers will measure the masses, ages, and chemical compositions of these galaxies with greater precision. Theorists will refine their models, testing different scenarios against the data. And slowly, a clearer picture will emerge. But here is what we already know. The universe is more complex than we thought. The early universe was more active, more dynamic, more capable of forming structure than our models predicted. Whether this requires minor adjustments or major revisions remains to be seen. But either way, we are learning. We are refining our understanding. We are doing science. And the James Webb Telescope, floating silently in the darkness 1.5 million kilometers from Earth, continues to stare into the abyss of cosmic time, sending back light that challenges everything we thought we knew. Each photon is a messenger from the ancient universe, carrying information that will reshape our understanding of existence itself. And we, here on this small blue planet, are privileged to receive these messages, to decode them, and to glimpse the universe as it truly is. Not as we wish it to be, but as it reveals itself to be. But let us step back from the immediate crisis and ask a deeper question. What does it mean for a scientific theory to be broken? This is not a semantic game. It cuts to the heart of how science actually works and how we should interpret moments like this one. When a newspaper headline screams that the Big Bang theory is broken, what is really being claimed? Is it that the universe did not begin in a hot, dense state? No. The evidence for that, the cosmic microwave background, the abundance of light elements, the expansion of space, remains overwhelming. Is it that the universe is not 13.8 billion years old? Not necessarily. The age estimate comes from multiple independent measurements that all converge on roughly the same number. What is actually being challenged is something more subtle and more profound. Our understanding of how structure emerges from chaos, how gravity sculpts matter over cosmic time, and how the fundamental forces and particles behaved in conditions we can never recreate in a laboratory. This distinction matters because it reveals something crucial about the nature of scientific knowledge. Science does not deal in absolute certainty. It deals in models, mathematical frameworks that describe observations and make predictions. A good model is not one that is eternally true. A good model is one that is useful, that explains a wide range of phenomena, and that can be tested and refined. Newton's law of universal gravitation was a good model. It predicted planetary orbits, explained tides, and allowed us to calculate the mass of the Earth. but it was not complete. It could not explain the precession of Mercury's orbit or the bending of light around the Sun. Einstein's general relativity is a better model. It explains everything Newton's model explained, plus phenomena Newton's model could not account for. But even general relativity is incomplete. It breaks down at singularities, inside black holes, and at the moment of the Big Bang itself. Someday, we will have a better model, one that unifies gravity with quantum mechanics. And that model, too, will eventually be superseded. This is not failure. This is progress. Each new model is a refinement, a closer approximation to reality. And the James Webb observations are forcing us to refine our cosmological model in real time. Now, consider what happens when a model encounters an anomaly. There are three possible responses. The first is to dismiss the anomaly as measurement error. This is often the correct response, especially in the early stages of a new observational campaign. Instruments malfunction, data gets misinterpreted, systematic errors creep in. But as more data accumulates, and as independent teams confirm the anomaly, this explanation becomes less tenable. The second response is to adjust the model, to tweak parameters, add new variables, or refine assumptions. This is the most common response, and it is usually successful. Most anomalies can be resolved with minor modifications, but sometimes the adjustments required are so extensive that they strain the model to its breaking point. And that brings us to the third response, to replace the model entirely, or at least to fundamentally restructure it. We are not yet at the third stage with the Big Bang model, but we are past the first stage. The James Webb anomalies are not going away. Multiple independent teams have confirmed them. The data quality is excellent. The statistical significance is high. So we are in the second stage, the stage of adjustment and refinement. And this is where things get interesting, because the adjustments being proposed are not trivial. They involve rethinking the nature of dark matter, the behavior of dark energy, the efficiency of star formation, and possibly even the laws of physics in the early universe. Let us explore one of these adjustments in detail. The idea that star formation in the early universe was fundamentally different from star formation today. In the present-day universe, when a gas cloud collapses to form stars, the process is inefficient. Only about 1 to 2% of the gas actually becomes stars. The rest is blown away by stellar winds, supernova explosions, and radiation pressure. This inefficiency is built into our models. It is based on observations of star-forming regions in nearby galaxies. But what if the early universe was different? What if, in the absence of heavy elements and dust, gas clouds could collapse more completely, converting a much higher fraction of their mass into stars? This is not a wild speculation. There are physical reasons to think star formation might have been more efficient in the early universe. Heavy elements and dust act as coolants, allowing gas clouds to radiate away energy and collapse. But they also create opacity, blocking radiation and creating pressure that resists collapse. In the pristine environment of the early universe, with no heavy elements and no dust, gas clouds would have been more transparent. Radiation could escape more easily. Clouds could collapse more completely. And the stars that formed would have been more massive, burning hotter and brighter. But there is a limit to how far you can push this argument. Even with perfect efficiency, even if every atom of gas became a star, you still need enough gas in the right place at the right time. And that brings us back to dark matter. Dark matter provides the gravitational scaffolding on which galaxies form. It clumps first, creating potential wells that attract normal matter. The rate at which dark matter clumps depends on its properties, its mass, its velocity, its interaction cross-section. If dark matter clumps faster than we think, galaxies can form earlier. But faster clumping requires either that dark matter particles are heavier, or that they interact more strongly, or that the initial density fluctuations were larger. Each of these possibilities has consequences that ripple through the entire cosmological model. Take the idea that dark matter particles are heavier. In the standard cold dark matter model, the particles are assumed to have masses in the range of 1 to 1,000 times the mass of a proton. But what if they are much heavier, millions or billions of times the mass of a proton? Such particles would clump very efficiently, forming dense halos early in cosmic history. But they would also affect the cosmic microwave background in specific ways, creating patterns that we can measure. And so far, those patterns have not been observed. This does not rule out heavy dark matter, but it constrains it. The particles cannot be too heavy, or we would have seen their effects already. Or consider the idea that dark matter interacts more strongly than we think. In the standard model, dark matter is _22 particles pass through each other without interacting, except through gravity. But what if dark matter particles can collide and scatter like atoms in a gas? This would change how dark matter halos form and evolve. In the early universe, when densities were higher, collisions would have been more frequent. This could have allowed dark matter to settle into denser configurations, providing stronger gravitational wells for normal matter. But it would also have affected the shapes of dark matter halos, making them rounder and less cuspy. And observations of galaxy rotation curves and gravitational lensing suggest that dark matter halos are quite cuspy, at least in the present-day universe. So self-interacting dark matter is constrained, though not ruled out. Then there is the possibility that the initial density fluctuations, the tiny quantum ripples in the fabric of space that seeded all structure, were larger than we think. These fluctuations are imprinted in the cosmic microwave background, and we have measured them with exquisite precision. But there is a subtlety here. The cosmic microwave background shows us fluctuations on large scales, scales of millions of light years. On smaller scales, scales of thousands or tens of thousands of light years, the fluctuations are harder to measure. What if, on these small scales, the fluctuations were larger than the standard inflationary model predicts? This could allow small dark matter halos to form earlier, which could then merge to form larger halos faster than expected. Some models of inflation do predict enhanced small-scale fluctuations, and these models are now being revisited in light of the James Webb data. But all of these adjustments share a common feature. They are ad hoc. They are designed to fix a specific problem without breaking everything else. And that is fine. Science often proceeds by ad hoc adjustments. But at some point, if you have to make too many adjustments, if you have to add too many new parameters, the model becomes unwieldy. It loses its predictive power. It becomes less a description of reality and more a collection of patches. And that is when scientists start to wonder if a more fundamental change is needed. So let us consider a more radical possibility, that the universe underwent a phase transition in its first few 100 million years, a transition that temporarily altered the laws of physics or the properties of particles. This is not as crazy as it sounds. We know the universe has undergone phase transitions before. In the first trillionth of a second after the Big Bang, the universe was so hot that the electromagnetic force and the weak nuclear force were unified. As the universe cooled, this symmetry broke, and the two forces separated. This phase transition released energy, driving a brief period of rapid expansion called inflation. Later, when the universe was a millionth of a second old, quarks combined to form protons and neutrons, another phase transition. And when the universe was 380,000 years old, electrons combined with nuclei to form neutral atoms, releasing the cosmic microwave background, yet another phase transition. Each of these transitions changed the behavior of matter and energy. Each left observable signatures. So it is not unreasonable to ask, could there have been another phase transition, one that we have not yet detected, that occurred in the first few 100 million years after the Big Bang? And could this transition have temporarily accelerated structure formation? One version of this idea involves the Higgs field. The Higgs field is responsible for giving particles their mass. In the very early universe, the Higgs field was in a high-energy state, and particles were massless. As the universe cooled, the Higgs field settled into its current low-energy state, and particles acquired mass. But what if this transition was not instantaneous? What if there was a period when the Higgs field was oscillating between states, or when it had a different value in different regions of space? This could have affected the masses of particles, which in turn would have affected how they interacted and how structures formed. If particles were lighter in the early universe, they would have moved faster, and dark matter would have been _23_ smoothing out small-scale structure. But if particles were heavier, dark matter would have been _24_ clumping more efficiently. Either way, the properties of the Higgs field could have influenced the formation of the first galaxies. Another version involves extra dimensions. String theory, the leading candidate for a theory of quantum gravity, predicts that space has more than 3 dimensions. The extra dimensions are thought to be, quote, 25, curled up so small that we cannot detect them. But what if, in the early universe, these extra dimensions were larger? What if they only compactified later as the universe cooled? This would have affected the strength of gravity. In a higher dimensional space, gravity spreads out over more dimensions, making it weaker. But as dimensions compactify, gravity becomes confined to 3 dimensions, making it stronger. If this transition happened in the first few hundred million years after the Big Bang, it could have temporarily enhanced the gravitational attraction between particles, allowing structures to form faster. These ideas are highly speculative. They are at the cutting edge of theoretical physics, where mathematics and philosophy blur together. But they are not untestable. If the Higgs field behaved differently in the early universe, it would have left signatures in the masses and abundances of particles, which we can measure in particle accelerators and in the cosmic microwave background. If extra dimensions compactified late, it would have affected the expansion rate of the universe and the growth of structure, which we can measure with telescopes. So even the most exotic ideas can be constrained by observation. Now, let us turn to a question that is often overlooked in discussions of cosmology. What role does technology play in shaping our understanding of the universe? The James Webb Space Telescope is not just a tool for gathering data. It is a lens through which we see reality, and the properties of that lens determine what we can see and what remains hidden. James Webb observes in the infrared, wavelengths longer than visible light. This is crucial for studying the early universe, because as space expands, light from distant objects is stretched to longer wavelengths, a phenomenon called redshift. Light that was emitted as ultraviolet or visible light billions of years ago arrives at Earth as infrared light today. Hubble, which observes primarily in visible and ultraviolet wavelengths, could see galaxies out to a redshift of about 11, corresponding to about 400 million years after the Big Bang. James Webb, with its infrared sensitivity, can see galaxies at redshift 13, 15, even potentially 20, corresponding to just 150 million years after the Big Bang. This is a game changer. It is like upgrading from a telescope that can see a few kilometers to one that can see across continents. But infrared astronomy is hard. Earth's atmosphere glows brightly in the infrared, drowning out faint signals from space. That is why James Webb is in space, orbiting the Sun at a point called L2, 1.5 million kilometers from Earth, where it is shielded from the Sun, Earth, and Moon. Even there, the telescope itself emits infrared radiation, because anything with temperature glows in the infrared. So James Webb is cooled to -233 degrees Celsius, just 40 degrees above absolute zero, using a massive sun shield the size of a tennis court. And its detectors are cooled even further, to -266 degrees Celsius, using liquid helium. This is engineering at the edge of what is possible. And yet, even with all this technology, there are limits. James Webb can detect galaxies at high redshift, but it cannot always measure their distances precisely. Photometric redshifts, estimates based on the colors of galaxies, are uncertain, with errors of 10 to 20%. Spectroscopic redshifts, measurements based on the wavelengths of specific spectral lines, are much more precise, but they require long exposure times and are only possible for the brightest objects. So there is a trade-off. We can survey large areas of sky quickly with photometry, finding many candidate high redshift galaxies. Or we can study a few objects in detail with spectroscopy, confirming their distances and properties. Both approaches are necessary, and both are being pursued. But here is the deeper point. Our understanding of the universe is always limited by our technology. Before Galileo pointed a telescope at the sky, we thought the universe consisted of the Earth, the Sun, the Moon, the planets, and the stars, all embedded in crystalline spheres. The telescope revealed moons orbiting Jupiter, phases of Venus, mountains on the Moon, and countless stars invisible to the naked eye. Each new generation of telescopes has revealed new phenomena: nebulae, galaxies, quasars, black holes, exoplanets, gravitational waves. And each revelation has forced us to revise our models. James Webb is the latest in this lineage. It is showing us a universe that is richer, stranger, and more complex than we imagined. But it is not the final word. Already, astronomers are planning the next generation of telescopes, ground-based observatories with mirrors 30 meters across, space telescopes that can directly image Earth-like planets around other stars, gravitational wave detectors that can sense the collisions of black holes billions of light-years away. Each of these instruments will reveal new mysteries, new anomalies, new challenges to our models. And that is how science progresses, not by reaching final answers, but by asking better questions. So where does this leave us, here in the middle of the story? We have seen the problem: galaxies that are too massive, too mature, too structured to exist so early in cosmic history. We have explored possible explanations: more efficient star formation, faster dark matter clumping, modified gravity, early dark energy, phase transitions, extra dimensions. We have examined the reaction of the scientific community: excitement, caution, anxiety, debate. And we have reflected on the nature of scientific knowledge itself: provisional, self-correcting, always subject to revision in light of new evidence. But we have not yet addressed the most profound question of all. What does this mean for us? Not for cosmologists, not for physicists, but for human beings trying to make sense of our place in the universe. That question, the existential philosophical dimension of these discoveries, is where we turn next. Because science is not just about understanding the universe, it is about understanding ourselves. I understand perfectly what you might be thinking right now. After everything we have discussed, the impossible galaxies, the theoretical adjustments, the exotic physics, you might be wondering, is this just another case of scientists getting carried away? Is this the modern equivalent of epicycles, those elaborate mathematical constructions medieval astronomers invented to preserve the Earth-centered model of the cosmos? Are cosmologists so invested in the Big Bang framework that they are willing to twist the theory into pretzels rather than admit it might be fundamentally wrong? This is not a straw man argument. This is a legitimate question, and it deserves a serious answer. Because the history of science is littered with examples of theories that were defended long past their expiration date, propped up by increasingly elaborate modifications until finally collapsing under their own weight. Ptolemy's geocentric model survived for 14 centuries by adding epicycles upon epicycles. The caloric theory of heat, the idea that heat was a fluid called caloric, persisted for decades despite mounting evidence against it. The steady-state model of the universe, which proposed that the cosmos had no beginning and maintained constant density through continuous creation of matter, was defended by prominent physicists well into the 1960s, even after the discovery of the cosmic microwave background made it untenable. So how do we know the Big Bang model is not heading down the same path? How do we distinguish between productive refinement and desperate rationalization? This is not just a philosophical question, it is a practical one, with real consequences for how we allocate research funding, how we train the next generation of scientists,
and how we communicate science to the public.
the answer lies in understanding what makes a scientific theory robust. A robust theory is not one that never encounters anomalies. Every theory encounters anomalies. A robust theory is one that makes multiple independent predictions, each of which can be tested separately. If the theory fails one test but passes 10 others, we adjust the theory to account for the failure while preserving what works. But if the theory starts failing multiple independent tests, if the adjustments required to fix one problem create new problems elsewhere, then we know we are in trouble. So, let us apply this standard to the Big Bang model. What are its independent predictions, and how well do they hold up? First, the expansion of space. In 1929, Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This is exactly what you would expect if space itself is expanding,
Carrying galaxies along with it.
This prediction has been tested countless times, with increasingly precise measurements, and it holds up. The expansion is real. Second, the cosmic microwave background. If the universe began in a hot, dense state, then as it expanded and cooled, there should have been a moment when it became transparent, when electrons combined with nuclei to form neutral atoms, releasing a flash of light that has been traveling through space ever since. This light should be visible today as a faint glow of microwave radiation coming from all directions, with a temperature of about 3 degrees above absolute zero. In 1965, Arno Penzias and Robert Wilson accidentally discovered this radiation. Its temperature is 2.7 degrees. Its spectrum matches a perfect blackbody to 1 part in 100,000. This is one of the most precise confirmations of any scientific prediction ever made. Third, the abundance of light elements. In the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion, protons and neutrons combined to form the nuclei of hydrogen, helium, and trace amounts of lithium and beryllium. The Big Bang model predicts specific ratios for these elements based on the density of normal matter and the expansion rate of the universe. Observations of the oldest stars and gas clouds confirm these predictions. About 75% of normal matter is hydrogen, about 25% is helium, and trace amounts are lithium, exactly as predicted. Fourth, the evolution of galaxy populations. If the universe has been expanding and cooling over time, then galaxies in the distant past should look different from galaxies today. They should be smaller, more irregular, more actively forming stars, and less chemically enriched. Observations confirm this. High redshift galaxies are indeed smaller, more chaotic, and bluer than nearby galaxies. The Hubble Deep Field, the Hubble Ultra Deep Field, and now the James Webb Deep Field all show this evolutionary trend. Fifth, the distribution of large-scale structure. The pattern of galaxy clusters, superclusters, and voids we see today should reflect the tiny density fluctuations imprinted in the cosmic microwave background. Computer simulations that start with these fluctuations and evolve them forward using the laws of gravity reproduce the observed large-scale structure with remarkable accuracy. The cosmic web, the filamentary network of galaxies stretching across billions of light-years, is a direct consequence of the initial conditions set by the Big Bang. So the Big Bang model passes 5 major independent tests. This is not a house of cards. This is a structure with multiple load-bearing pillars. And this is why cosmologists are not abandoning the model in response to the James Webb anomalies. The anomalies challenge one aspect of the model, the timeline and efficiency of galaxy formation. But they do not invalidate the expansion of space, the cosmic microwave background, the abundance of light elements, the evolution of galaxies, or the large-scale structure. The foundation remains solid. What is being questioned is the detailed architecture built on that foundation. But let us push harder on this. Let us consider the most radical interpretation of the James Webb data. that the universe is significantly older than 13.8 billion years. Could this be true? And if so, what would it mean? An older universe would solve the James Webb problem immediately. If the universe is 15 billion years old, or 17 billion, or 20 billion, then there is more time for galaxies to form, more time for stars to evolve, more time for structures to mature. The impossible galaxies become merely improbable. The crisis evaporates. But an older universe creates new problems. The age of the universe is not a free parameter we can adjust at will. It is tightly constrained by multiple independent measurements. The cosmic microwave background tells us how long ago the universe became transparent. The expansion rate tells us how long it has been expanding. The ages of the oldest stars tell us how long matter has been forming stars. All of these measurements converge on 13.8 billion years, give or take a few hundred million. To make the universe significantly older, you would have to revise all of these measurements simultaneously,
in a coordinated way.
You would have to explain why the cosmic microwave background looks the way it does if the universe is older. You would have to explain why the oldest stars are not older. You would have to explain why the expansion rate measurements are systematically wrong. This is not impossible, but it is difficult. It requires a conspiracy of errors, or a fundamental misunderstanding of multiple independent phenomena. And this is why most cosmologists are not seriously considering the idea that the universe is much older. It solves one problem, but creates many others. So, if the universe is not older, and if the Big Bang framework is fundamentally sound, then we are left with the conclusion that something about the early universe, the efficiency of star formation, the behavior of dark matter, the properties of dark energy, or the laws of physics themselves, was different from what we assumed. And this brings us to the heart of the matter:
The limits of extrapolation. All of our cosmological models are based on extrapolating known physics into extreme conditions. We take the laws of gravity, thermodynamics, quantum mechanics, and particle physics as we understand them today, and we apply them to the universe as it was 13 billion years ago, when it was 1,000,000 times denser and 1,000,000 times hotter. This is an audacious extrapolation. We are assuming that the laws of physics do not change over cosmic time, that they apply in conditions we can never recreate in a laboratory, that they hold at energy scales far beyond anything we can test with particle accelerators. Most of the time, this extrapolation works. The cosmic microwave background, the abundance of light elements, the large-scale structure, all of these confirm that the laws of physics we know today also applied in the early universe. But the James Webb anomalies suggest that somewhere, somehow, our extrapolation is breaking down. Not catastrophically, the broad framework still holds, but subtly, in ways that matter for the formation of the first galaxies. This is not a failure of science. This is science working exactly as it should. We make predictions based on our best understanding. We test those predictions with observations. When observations disagree with predictions, we refine our understanding. The process is iterative, self-correcting, and ultimately convergent. We get closer to the truth with each iteration, even if we never reach absolute certainty. But here is where things get philosophically interesting. What does it mean to say we are getting closer to the truth? Truth about what? The universe does not care about our models. It does not care whether we understand it or not. It simply exists, doing whatever it does, following whatever rules it follows. Our models are human constructs, maps we draw to navigate reality. And like all maps, they are simplifications. They leave out details, they distort proportions. They emphasize some features and ignore others. A map of a city does not show every brick in every building, every leaf on every tree. It shows streets, landmarks, neighborhoods, the features that matter for navigation. Similarly, a cosmological model does not describe every particle in the universe, every quantum fluctuation, every gravitational interaction.
It describes the large-scale behavior, the statistical averages, the emergent patterns. And just as a city map becomes less accurate as you zoom in, eventually you need a building plan, then a blueprint, then a molecular diagram. A cosmological model becomes less accurate as you probe finer details. The Big Bang model is extraordinarily accurate at describing the universe on scales of billions of light-years and timescales of billions of years. But on scales of individual galaxies and timescales of millions of years, the model is less precise. It relies on approximations, on averaged properties, on simplified physics. And this is where the James Webb anomalies are biting. They are probing a regime, the first few 100 million years, the formation of the first galaxies, where our approximations may not be good enough. So what do? We refine the map. We add more detail. We measure more carefully. We test more rigorously. And we remain humble about the limits of our knowledge. This humility is crucial because it is what separates science from dogma. A dogmatic system claims to have final answers, absolute truths that cannot be questioned. Science makes no such claim. Every scientific theory is provisional, subject to revision, open to challenge. This is not a weakness. It is science's greatest strength. It is what allows science to adapt, to grow, to improve over time. And this is why the James Webb discoveries, far from undermining science, actually demonstrate its power. Science is not a collection of facts to be memorized. It is a method for interrogating reality, for testing ideas against evidence, for discarding what does not work and keeping what does. The fact that cosmologists are willing to question their own models, to consider radical alternatives, to follow the evidence wherever it leads, this is science at its best. But let us be honest about something else. This process is messy, it is slow, it is contentious. Scientists disagree with each other, sometimes vehemently. Papers are published, criticized, retracted, revised. Theories are proposed, tested, modified, abandoned. From the outside, this can look like chaos. It can look like scientists do not know what they are talking about, that they are just making things up as they go along. And in a sense, they are. But making things up is not the same as making things up arbitrarily. Every idea is constrained by evidence, by mathematics, by consistency with other established theories. The space of possible explanations is vast, but it is not infinite, and over time, as more data accumulates, that space narrows. Wrong ideas are eliminated. Correct ideas survive and are refined. The process converges on truth, even if it never reaches it completely. Now, let us consider a specific example of this process in action: the Hubble tension. For the past decade, astronomers have been measuring the expansion rate of the universe using two different methods. One method uses the cosmic microwave background, the afterglow of the Big Bang. By analyzing the pattern of hot and cold spots in this radiation, cosmologists can infer the expansion rate in the early universe and extrapolate it to today. This method gives a value of about 67 kilometers per second per megaparsec. The other method uses nearby supernovae and other standard candles, objects whose intrinsic brightness is known, allowing us to calculate their distance by measuring how bright they appear. By measuring the distances and redshifts of these objects, astronomers can directly measure the expansion rate today. This method gives a value of about 73 kilometers per second per megaparsec. 6 kilometers per second per megaparsec might not sound like much, but it is a 9% discrepancy, and it is statistically significant. Both measurements have been repeated by multiple independent teams using different instruments and different analysis techniques. The discrepancy is real, and it has persisted for years, despite intensive efforts to find systematic errors that could explain it. This is a crisis. Not as dramatic as the James Webb anomalies, but in some ways more fundamental, because it suggests that either our measurements are wrong or our understanding of cosmic expansion is incomplete. And here is the key point. The Hubble tension and the James Webb anomalies might be related. If the expansion rate in the early universe was different from what we think, if dark energy behaved differently, if there was an extra component of energy density we have not accounted for, then both problems could be solved simultaneously. An early dark energy model, for example, could increase the expansion rate in the early universe, resolving the Hubble tension, while also giving structures more time to form before expansion pulled them apart, resolving the James Webb anomalies. This is how science progresses. Separate anomalies, initially thought to be unrelated, turn out to be pieces of the same puzzle. A single modification to the model explains multiple observations. And when that happens, confidence in the modification increases. It is no longer an ad hoc fix for one problem. It is a coherent explanation for multiple problems. But we are not there yet. Early dark energy models are promising, but they are not yet confirmed. They make predictions that can be tested with future observations. Measurements of the cosmic microwave background at higher precision, observations of the large-scale structure at higher redshift, measurements of gravitational waves from the early universe. Over the next decade, as these observations are made, we will know whether early dark energy is the right explanation, or whether we need to look elsewhere. And this brings us to the final point I want to make in this section: the importance of time. Science is not fast. It does not deliver instant answers. It requires patience, persistence, and a willingness to live with uncertainty. The James Webb Space Telescope launched in December of 2021. It began science operations in July of 2022. We are now in early 2026, less than 4 years into its mission. It is designed to operate for at least 10 years, possibly 20. We are still in the early stages of data collection. The anomalies we are discussing now are based on preliminary observations, photometric redshifts, small samples. Over the coming years, as more data accumulates, as spectroscopic follow-up confirms or revises the photometric redshifts, as larger samples allow for statistical analysis, the picture will become clearer. Some of the anomalies will disappear. Some galaxies that appear to be at redshift 13 will turn out to be at redshift 5, closer and less problematic. But some anomalies will remain, and new ones will emerge. And slowly, painstakingly, the scientific community will converge on an explanation. It might be a minor adjustment to existing models. It might be a major revision. But whatever it is, it will be based on evidence, tested against multiple independent observations, and subject to ongoing scrutiny. This is the reality of science. It is not a smooth, linear march toward truth. It is a messy, iterative process of trial and error, of hypothesis and test, of debate and revision. And it requires a tolerance for ambiguity, a comfort with uncertainty that is often at odds with the human desire for clear, definitive answers. But here is the paradox. It is precisely this tolerance for uncertainty that makes science so powerful. By admitting what we do not know, by remaining open to revision, by following the evidence wherever it leads, science has given us the most accurate and reliable understanding of the natural world that humanity has ever achieved. It has taken us from a geocentric cosmos to an expanding universe of 2 trillion galaxies. It has revealed the quantum nature of matter, the relativity of space and time, the evolution of life, the structure of DNA, the existence of black holes and gravitational waves. And it has done all of this not by claiming absolute certainty, but by embracing doubt, by questioning assumptions, by testing ideas against reality. The James Webb Telescope is the latest instrument in this grand project. It is showing us a universe that challenges our models, that forces us to think harder and deeper, that reminds us how much we still have to learn. And that is not a crisis. That is an opportunity. An opportunity to refine our understanding, to discover new physics, to glimpse aspects of reality we never imagined. So when you hear that the James Webb Telescope has broken the Big Bang Theory, understand what that really means. It does not mean the Big Bang did not happen. It does not mean cosmologists are clueless. It means we are learning. It means the universe is more complex than we thought. It means there is still work to do, still mysteries to solve, still frontiers to explore. And that, ultimately, is what makes science so thrilling.
Not the answers we have found, but the questions we have yet to ask.
But now, let us step away from the equations, the redshifts, the competing models. Let us step away from the technical debates and ask a question that might seem out of place in a discussion of cosmology, but is perhaps the most important question of all. Why does any of this matter? You are sitting here, on a planet orbiting an ordinary star in an ordinary galaxy, watching photons dance across a screen, learning about galaxies that existed 13 billion years ago. These galaxies are so far away that their light has been traveling toward you for almost the entire history of the universe. By the time their light reaches your eyes, those galaxies have long since evolved, merged, perhaps been torn apart by collisions or swallowed by larger structures. The light you see is a ghost, an echo, a message from a universe that no longer exists in that form. And yet, somehow, this matters to you. Somehow, the fact that these ancient galaxies are slightly more massive than our models predicted, that they formed slightly earlier than we thought possible, that they challenge our understanding of cosmic evolution. Somehow, this captures your attention, sparks your curiosity, makes you wonder about the nature of reality itself. This is not a trivial thing. You could be doing anything else with your time. You could be focused entirely on your immediate surroundings, on the practical concerns of daily life, on the people and places and problems that directly affect you. And yet, here you are, thinking about the early universe, about dark matter and dark energy, about the limits of human knowledge. Why? The answer, I think, lies in something fundamental about human consciousness. We are not just creatures who exist in the universe. We are creatures who know we exist in the universe. We are matter that has become aware of itself. Atoms that have organized themselves into patterns complex enough to contemplate their own origins. And this self-awareness brings with it an insatiable curiosity, a need to understand not just how things work, but why they are the way they are, what it all means, where we fit in the grand scheme of existence. The James Webb discoveries speak to this deep human need. They remind us that the universe is not a static backdrop against which our lives unfold. It is a dynamic, evolving system with a history, a story that stretches back to the beginning of time itself. And we are part of that story. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces, scattered across space by supernova explosions, and eventually incorporated into the gas cloud that collapsed to form our solar system.
You are made of stardust.
This is not a metaphor. This is literal truth. But the connection goes deeper than that. The laws of physics that govern the formation of galaxies also govern the chemistry of life. The same quantum mechanics that determines how electrons orbit atomic nuclei also determines how molecules bond, how DNA replicates, how neurons fire in your brain. The same gravity that pulls galaxies together also keeps your feet on the ground, keeps the Earth in orbit around the Sun, keeps the Sun in orbit around the center of the Milky Way. You are not separate from the universe. You are an expression of it, a local manifestation of the same physical laws that operate everywhere, at all scales, at all times. And this is why cosmology matters. It is not just about understanding distant galaxies. It is about understanding the context in which we exist. It is about tracing the chain of causation that leads from the Big Bang to this moment, from the first quantum fluctuations to the emergence of stars, planets, life, consciousness, and civilization. It is about recognizing that we are not accidental, not separate, not insignificant, but integral, connected, part of a vast cosmic process that has been unfolding for 13.8 billion years. The James Webb anomalies in this light are not just technical problems for cosmologists to solve. They are invitations to wonder, to question, to push the boundaries of human understanding. They remind us that the universe is stranger than we imagined, that our models are incomplete, that there is always more to learn. And they challenge us to remain humble, to admit what we do not know, to resist the temptation to claim certainty where none exists. So let us be honest about what we do not know. We do not know what dark matter is. We have never detected a dark matter particle, despite decades of searching. We infer its existence from gravitational effects, but we do not know its nature, its properties, its origin. It could be a new type of particle, or it could be something else entirely: modified gravity, extra dimensions, a misunderstanding of how gravity works on cosmic scales. We simply do not know. We do not know what dark energy is. We know it is causing the expansion of the universe to accelerate, but we do not know why. It could be a property of space itself, a quantum field that permeates the vacuum, or it could be something more exotic, a fifth force, a sign that general relativity breaks down on cosmological scales, a hint of physics beyond the standard model. We do not know. We do not know how the first stars formed. We have models, simulations, educated guesses. But we have never observed a population 3 star, a star made of pure hydrogen and helium, with no heavy elements. We do not know how massive they were, how long they lived, how they affected their surroundings. We are extrapolating from theory, not from observation. We do not know how supermassive black holes formed. Every large galaxy has a black hole at its center, with a mass millions or billions of times that of the Sun. But we do not know how these black holes grew so large so quickly. Did they form from the collapse of massive stars? From the direct collapse of gas clouds? From the merger of smaller black holes? We have hypotheses, but no definitive answers. We do not know whether the laws of physics have always been the same. We assume they have, because that is the simplest assumption, and it has worked well so far. But we have no way to test this assumption directly. We cannot go back in time and measure the strength of gravity in the early universe. We can only infer it from observations, and those observations are always subject to interpretation. We do not know whether our universe is the only universe. The equations of quantum mechanics and general relativity allow for the possibility of multiple universes, each with different properties, different laws of physics, different values of fundamental constants. This is not science fiction. It is a serious theoretical possibility, discussed in peer-reviewed journals by respected physicists. But we have no way to test it, no way to observe other universes, no way to know if they exist. It remains speculation, tantalizing, but unproven. We do not know what happened at the moment of the Big Bang itself. General relativity predicts a singularity, a point of infinite density and infinite curvature, where the laws of physics break down. But we know this prediction cannot be correct because it leads to nonsensical results. We need a theory of quantum gravity to describe what really happened, and we do not have one. String theory, loop quantum gravity, causal set theory. These are all attempts to build such a theory, but none has been confirmed by experiment. The moment of creation remains a mystery. We do not know whether time had a beginning. The Big Bang marks the beginning of our observable universe, but it might not be the beginning of time itself. Time could have existed before the Big Bang, in a previous phase of the universe, or in a larger multiverse of which our universe is just one part. Or time itself could be an emergent phenomenon, not fundamental, arising from something deeper. We do not know. We do not know whether the universe will end. Current observations suggest the expansion will continue forever, accelerating under the influence of dark energy, until galaxies are so far apart that they can no longer see each other, until stars burn out and black holes evaporate, until the universe reaches a state of maximum entropy, a cold, dark, empty void. But this prediction depends on assumptions about dark energy that might be wrong. The universe could recollapse in a big crunch. It could undergo a phase transition that changes the properties of space itself. It could be cyclic, expanding and contracting in an endless rhythm. We do not know. And here is the most profound thing we do not know. We do not know why there is something rather than nothing. Why does the universe exist at all? Why are there laws of physics? Why is there matter and energy, space and time, structure and complexity? These are not scientific questions in the usual sense. They cannot be answered by observation or experiment. They are philosophical questions, metaphysical questions, questions that probe the very foundations of existence. And yet, they are questions that science inevitably leads us to, because the more we understand about how the universe works, the more we are confronted with the mystery of why it works at all. This is not a failure of science. This is the boundary where science meets philosophy, where empirical investigation meets existential wonder. And it is a boundary worth contemplating, because it reminds us that knowledge is not the same as understanding, that explanation is not the same as meaning, that we can describe the universe in exquisite mathematical detail without ever fully grasping why it is the way it is. But perhaps that is as it should be. Perhaps the universe is not meant to be fully understood, not by creatures like us, with our limited lifespans and finite brains. Perhaps the best we can do is to keep asking questions, keep making observations, keep refining our models, keep pushing the boundaries of knowledge a little further with each generation. And perhaps that is enough. Perhaps the journey is more important than the destination, the search more meaningful than the answer. Do you remember how we began? With light that has traveled for over 13 billion years, carrying information that should not exist, showing galaxies that break the rules of cosmic evolution. We have journeyed through the technical details, the competing theories, the scientific debates. We have confronted the limits of our models and the uncertainty of our knowledge. And now, at the end, we return to where we started, but with a deeper understanding, a richer perspective, a greater appreciation for the complexity and mystery of existence. Those impossible galaxies are still there, still challenging our assumptions, still forcing us to think harder. The scientists are still working, still analyzing data, still proposing and testing new ideas. The James Webb telescope is still observing, still sending back images that reshape our understanding of cosmic history. And you are still here, still curious, still wondering about your place in this vast, ancient, evolving universe. And that curiosity, that willingness to ask questions, to seek answers, to confront the unknown, is perhaps the most remarkable thing of all. Because in a universe governed by entropy, where everything tends toward disorder and decay, where stars burn out and galaxies fade and even black holes eventually evaporate, in such a universe, the emergence of consciousness, of intelligence, of beings capable of understanding their own origins is nothing short of miraculous. You are a pattern of atoms that has become aware of itself. You are matter that has organized itself into a form complex enough to contemplate the nature of matter. You are the universe looking at itself, asking questions about itself, trying to understand itself. And in doing so, you are participating in something profound, a cosmic process of self-discovery that has been unfolding since the first stars ignited, since the first galaxies formed, since the first molecules capable of replication emerged in some primordial ocean on some distant world. The James Webb discoveries remind us that this process is ongoing, that the universe is still revealing itself, still surprising us, still challenging us to expand our understanding. They remind us that science is not a collection of final answers, but a method for asking better questions. They remind us that uncertainty is not weakness, but honesty. They remind us that the universe does not owe us easy explanations, that reality is under no obligation to conform to our expectations, that the cosmos is stranger and more wonderful than we can imagine. So when you look up at the night sky, when you see the faint glow of distant galaxies, when you think about the light that has traveled billions of years to reach your eyes, remember that you are not just observing the universe. You are part of it. You are connected to it in ways both physical and profound. The atoms in your body were forged in stars. The patterns in your brain reflect the patterns in the cosmos. The questions you ask are the universe asking questions about itself. And perhaps, in the end, that is the deepest answer we can give to the question of why any of this matters. It matters because we are here to witness it, to understand it, to marvel at it. It matters because consciousness has emerged from unconscious matter, because intelligence has arisen from random processes, because meaning has been created in a universe that began without meaning. It matters because we can look at those impossible galaxies, those rule-breaking structures, those challenges to our models, and instead of turning away, instead of clinging to comfortable certainties, we can lean in, ask harder questions, seek deeper understanding. The universe is 13.8 billion years old, or perhaps older. It contains 2 trillion galaxies, or perhaps more. It is governed by laws we are still discovering, shaped by forces we do not fully understand, filled with mysteries we have barely begun to explore. And you are a part of this vast cosmic story, a brief but brilliant flash of consciousness in an ocean of space and time. The James Webb Telescope has not broken the Big Bang Theory. It has done something far more important. It has reminded us that the universe is still full of surprises, that our understanding is still incomplete, that there is still so much to discover. And in doing so, it has given us the greatest gift science can offer. Not certainty, but wonder. Not final answers, but better questions. Not the end of the journey, but an invitation to continue exploring, to keep searching, to never stop asking why. Because in the end, the most important thing is not what we know, but that we keep trying to know more. Not that we have all the answers, but that we have the courage to admit when we do not. Not that the universe makes sense to us, but that we have the audacity to believe it can, the humility to accept when it does not, and the persistence to keep looking anyway. The light from those ancient galaxies is still traveling through space, carrying messages we are only beginning to decode. And somewhere, 13 billion years from now, if consciousness still exists in whatever form the universe allows, perhaps other beings will look back at our time, at our discoveries, at our struggles to understand, and they will see us as we see those early galaxies, as pioneers, as explorers, as the first tentative steps in a journey that has no end. That is the true meaning of the James Webb discoveries. Not that we were wrong, but that we are learning. Not that the universe is broken, but that it is more magnificent than we imagined. Not that science has failed, but that it is working exactly as it should, questioning, testing, revising, growing, forever reaching toward a truth that recedes even as we approach it, forever chasing a horizon that expands with every step we take. And that is enough. That is more than enough. That is everything.